Hi dears, welcome to my channel. Today we are discussing class 9, 10th lesson, work and energy. It's very simple lesson. Some concepts you have to understand about work, energy as well as power. Okay ma? So before that we have to see the question time of 9th lesson. What was the lesson? It was gravitation. There I have asked you 3 questions. Here it's the time to answer. The questions goes like this. Numerical value of capital G is. Okay, what is the numerical value of capital G? 6.67 into 10 raised to minus 11 Newton meter square per kilogram square. Then the second one is gravitational force is always dash force. Which kind of force is the gravitational force, ma'am? Is it attractive or repulsive? It is always attractive force. And the third one is acceleration due to gravity is maximum at dash. Is the acceleration due to gravity maximum at equator or at poles? It is maximum at poles. These were the questions and we have answered it. Now we are going to have a quick look about work and energy. What is work? All the time we used to say, I have done this much work, I have done that much work and all. So what is work according to physics? According to physics, work is done only when a force is applied on that object, and if that object has been displaced to a certain extent, then only we can say a work is done by that object. Did you get, ma'am? If a force of 1 Newton, if we are applying a force of 1 Newton over and consider this as an object, okay? This is an object. And if I am applying a force on this object, and if this object is moving to a particular distance, I can say what? Work is done by me. Okay, so this is work. So what all things it depends on? It depends on force and it depends on displacement. So can I ask you one thing? If I am pushing a wall, can I say work is done by me? I can't say, because even though I am applying force on the wall is not moving, isn't it? The wall is not displacing to a particular extent, or it is not moving it's not changing its position. So I can't say that I have done any work. Okay, did you get the point? Force has to be applied and at the same time there should be a displacement on that object, on which object we are applying. Okay, ma'am? So this is said to be what work. So what is the SI unit of work? Or what is the work depends on? The work is depending on force as well as displacement. So what is the SI unit? SI unit is the SI unit of force as well as SI unit of displacement. What is the SI unit of force? It is Newton. What is the SI unit of displacement? It is meter. So what is the SI unit of work? Newton meter. Or there is one more term, that is joule. Joule. It is not joule. It is only joule. Okay. So SI unit of work can be Newton meter or joule. Okay. So can you define 1 joule? Yes, easily I can define 1 joule. What is 1 joule? 1 joule, we can say that 1 joule is work. 1 joule of work is done when force of 1 Newton is applied on an object, and if that object is displaced along 1 meter in the direction of force, we can say 1 joule of work is done. Okay? Force of 1 Newton as well as displacement of 1 meter. This thing has to be happened on that particular object. So what happens? We can say that 1 joule of work is done on that particular object. Okay, ma? Works are of different types. 3 types of work mainly the things are. That is positive work, negative work and zero work. Work can be positive work, negative work and zero work. How or by what way we can say the work is positive? Or by what way we can say it is negative, and how can we say it is zero? Consider, okay, a block, rectangular block. Okay, if I am applying force on a particular direction, F, and if it is displacing in the direction of force, we can say, what we can say? This is the displacement, right? Yes. If the force is applied in a particular direction and if the displacement has been happened to the same object, so we can say the work is then said to be positive. How? W is equal to F cross S. Vector. Force is vector quantity, displacement is a vector quantity. So obviously work is also a vector quantity. So what is W? W is equal to F S cos theta. What is theta? Theta is the angle between force and displacement. Here force is in a particular direction and S is also in the same direction. So what will be the theta value? Theta value will be 0 in this case. That is F S cos 0. What is cos 0? Cos 0 is 1, isn't it? So it is equal to Fs, positive Fs. In the case, if the object is moving in the direction of the force applied, we can say W is equal to Fs, that is positive Fs. Or we can say work is said to be positive. Okay, did you get ma? Now we have to see the negative work. The same object is there, and if I am applying force in a particular direction and instead of moving in this side, if the object has moved in this side, S. Force is applied in a particular direction, but the object is moving in the opposite direction. Is it possible? Yes, it is of course possible. If a table is there and if I am pushing from one side and two gents are pushing from the opposite side, what will happen? Even though I am applying force in a particular direction, the table will be moving in the opposite direction, isn't it? So it is also possible. In this case, W is equal to F S cos theta. What is the value of theta? Theta is 180 degree, isn't it? Because force in this direction and displacement in this direction. So what will be the angle? 180 degree. Cos 180 is what, ma? It is negative 1, isn't it? So it's equal to minus or Fs cos 180 is equal to minus Fs. In this case, what? In this case, the work done is negative. Negative work is done on that. Okay. And the third case where the work done is 0. How can it be possible? Let's see. See, this is the object, and if I am applying force in a particular direction, F is applied, but the displacement is happening in this direction. So what will be theta value? This is the angle, isn't it? Force, and this is displacement. So what is the angle? Theta. Theta is equal to 90 degree. So what is work done? W is equal to F S cos 90. What is the value of cos 90? Cos 90 degree is 0, isn't it? So F S into 0 is equal to 0. In this case, even though force is applied and displacement has been happened, we can say the work done is 0. Is there any case? Yes, cases are there. If I am tying a stone over a rope and if I am moving it in a circular manner, the work done on that stone will be 0. Because the force, in the which direction the force is applying, centripetal force is acting, isn't it? So the force is applying in the direction towards my hand. And what will be the displacement? The displacement of the stone is always tangent. The displacement will be always tangent. This is the stone. This is the stone. This is the stone. It will be in a circular manner, isn't it? It will be in a circular manner if I am circulating it. But what will be the direction of the stone? If I am throwing it away, it will be moving in this manner. This is 90 degree. If I am throwing in here, it will be moving in this manner. So again 90 degree, 90 degree. So this is the displacement. This is S and this is F. In this case, what ma? In this case, work done is said to be 0. Okay? Or we can say if a porter is carrying a heavy load on his head and if he is moving in a particular direction or if he is moving in a straight line, the work done is said to be 0 because weight is there on the head and the force is acting downwards due to gravity. The force is acting, but the displacement is happening in the perpendicular manner. That is, the displacement is in the horizontal line and the force is in the vertical line. In this manner, in this case, what happens? We can say the work done is said to be 0. Okay. Not only that, work can be 0 if force is 0 or the displacement is 0 also. Okay. So in what all cases we can say the work done is 0. If F is 0, we can say the work done is 0. If S is 0, in that case also work done is 0. And if F and S are not 0 in the values, but still we can say work done is 0 if and only if F is perpendicular to S. Okay. Now we are moving to see what are the conditions needed for the work to be done. What are the 3 conditions needed for the work to be done? 3 conditions are: the force has to be applied. Second one, the object has to be displaced. And the third one, the force as well as displacement are not perpendicular to each other. Okay. So what are the 3 conditions needed for the work? The force must be applied, the displacement has to be happened, and if force and displacement are not perpendicular to each other, then only we can say a work is done on a particular object. Okay, ma'am. Now I think the work is clear for you. Now we are going to see about energy. Now we are moving to see about energy. Up to this section we were discussing what work. So what is energy? Energy is the ability to do work or capacity to do work. Am I capable to do work? Then I can say that I am having energy. Okay. So this is energy. Is energy equivalent to work? Work and energy are not equal, but work is equivalent, almost equivalent to energy. Equivalent to work. That's why the unit of energy is same joule. What is the unit of work? It is joule, and unit of energy is joule. So how can we define 1 joule in terms of energy? 1 joule of energy is equal to 1 joule of work done. With 1 joule of energy, we can do 1 joule of work. Okay? With 1 joule of energy, 1 joule of work can be done. Okay, ma'am? So that is about the energy. Here, what are the types of energy? Is there only one type of energy? No, there are various types of energy, to say chemical energy, mechanical energy, solar energy, heat energy, light energy, sound energy, all many types of energies are there. But you should know one thing, that is energy is neither created nor destroyed, but can be transformed from one form to another. This is the truth. In the universe, in the beginning, how much energy was there? Now also the same energy is there prevailing, and this same energy will be there after generations. Okay, ma? Energy can neither be created nor be destroyed, but can be interconvertible. It can be converted from one form to another form. Okay, I had food. Okay, so with this energy, I am speaking to you. When I have taken the food, that energy has been chemical energy. That energy is coming out in the form of sound energy. Okay, did you get, ma'am? To say if solar panels are there, solar energy is grasped inside, and solar energy is converting into electrical energy, and electrical appliances are working with that. So solar energy is converted into electrical energy. Now when I am switching on the light is glowing. Means what? Electrical energy was there initially. That electrical energy has been converted into light energy as well as heat energy. Did you get, ma? So one form of energy is changing into another form, which doesn't mean that energy is creating. Energy is not getting created. Energy cannot be destroyed also. So energy is changing from one form into another. This is law of conservation of energy. Did you get, ma? Now the important terms. When we are saying about the energy, one important term you have to know, that is mechanical energy. Every object, due to its position or due to its motion, is possessing some kind of energy. This energy is called what, ma? Mechanical energy. Energy possessed by an object due to its position or due to its motion is called what, ma? It is mechanical energy. And mechanical energy is divided divided into two. What are they? Kinetic energy as well as potential energy. Energy possessed by the object due to its motion is what, ma? It is kinetic energy. And energy possessed by an object due to its position is called what, ma? Potential energy. Position, potential. Popo. So this is potential energy and this is due to motion, kinetic energy, and due to position is potential energy. Going to see the mathematical derivation of kinetic energy as well as potential energy. What it is? How can we define? Okay. Whatever it is, kinetic energy or whatever energy is what, ma? Work done. Work done. It is equivalent to work done. So what is work done formula? Force into displacement, isn't it? So it is equal to force into displacement. What is the, how can we define force? Mass into acceleration is force, isn't it? So F is equal to ma. And displacement can be is S, isn't it? So kinetic energy is equal to MAS. MAS. What is S over here? We have learned laws of kinematics, isn't it? V square minus U square is equal to 2AS. Do you remember? We have learned it, right? So what is S? Can you derive S out from it? So S will be what, ma? V square minus U square divided by 2A. Isn't it? So instead of S, we can apply here. That's equal to M into A into V square minus U square divided by 2A. This A and A got cancelled. Is equal to M V square minus U square by 2. V is the final velocity and U is the initial velocity. Consider the object is starting from rest. So what will be the initial velocity? It will be 0 because starting from rest, so it will be 0. So it is equivalent. So the value will be is equal to half into M V square. This is what, ma? This is equation for kinetic energy. What is the equation for kinetic energy? Ke is equal to half mv square. Okay, this is the equation for the kinetic energy. Now, how it is derived? Only when the object is moving from the rest, we got the equation of kinetic energy. So, what we are understanding? If the object is in motion, that object possesses kinetic energy. Okay. Now, we are moving to see about the potential energy. What is potential energy? If the object is at a rest and if it is in a particular position, we can say potential energy is there. So, if this is the ground level and if the object has been raised to a particular level, position is changed, isn't it? Position is not in rest but it is having in a particular position. And if there is height, h is the height which to which the object is raised. Okay. Again, we can say potential energy is equal to what, ma? Force into S. Here S is height. So, is equal to F into H. Because displacement is not horizontally but it is vertically. That's why S has been replaced by H. Then what is S? F. F is, here the object is raised. Means what? It is depending on the gravity. F is equal to MA, but here A has been changed to G because the object is in depending on gravity. So it is equal to, F is equal to mg into h. That's equal to mg h. This is what? This is the potential energy equation derivation of the potential energy. So what is the potential energy? Potential energy is equal to mgh if the object is raised to a height of h. Okay, and what is the kinetic energy? It's equal to half mv square if the object is moving from rest. Okay, these are the conditions for potential energy as well as for kinetic energy. Now we are looking for one thing, that is, how can you prove that the total energy of an object remains same? So how can we prove? Now we are going to prove it. Okay, we have discussed about the kinetic energy and potential energy. In what all places we can see the potential energy? Potential energy can be seen. The best example is the water. which is reserved in dams. Okay, the water which is in dams are having the potential energy maximum. And the second is the springs. If the spring is compressed, then due to its position, it is having energy. When the spring is released, this potential energy will be fully changed into kinetic energy. And in that case, when the dams are opened, the water which is having the potential energy will be transformed into kinetic energy because it will be flowing, isn't it? So the water will be starts moving. So this potential energy will be decreased and the kinetic energy will be increased. So what you are understanding is, if the potential energy is maximum, the kinetic energy will be zero. And if the kinetic energy is maximum, the potential energy will be zero. And in all the cases, total energy will be conserved and the total energy remains constant. Now we are proving that the total energy is constant. How can we prove it? Consider this is the ground and consider a ball. This is the ball and this is over a height h. This is the height possessed by the ball from the ground. So, and the ball is allowed to fall down. The ball is allowed to fall down. The ball is coming down to the ground. We are considering a point also. This as a point. So, this point as A, and when it is touching the ground, we are considering it as B, and a point in which the ball is there at particular instant, it is considered as C. So, we have to prove that total energy at A is equal to total energy at B and it is also equal to total energy at C. Okay, this is the one we have to prove. So, the first case, that is A at position A. What is the case at position A? When the ball is in position A, is it having potential energy or kinetic energy maximum? If any object is away from the gravity and if it is keeping constant, we can say potential energy is maximum in that case. So this object at a particular distance from the ground possesses maximum potential energy, having potential energy maximum. Is there any kinetic energy? Kinetic energy is 0. Okay, so what will be the total energy? Total energy is potential energy plus kinetic energy. That's equal to, what is potential energy? It is mg, as the height is h, we can say h plus 0 is equal to mgh. Did you get, ma'am? At position A, this is the total energy. Okay, this is mgh. Okay, now at position B. At position B, what happens to the object at position B? When the object is released from that point, it will be coming down. As it is coming down, its velocity will be increasing, isn't it? The velocity will be increasing means what? Kinetic energy starts increasing, but potential energy is going to be 0. And just that point at which if the object is touching the ground, it will be possessing maximum kinetic energy. Okay. So at position B, when it is just touching the ground, kinetic energy is maximum. And what will be the potential energy? Potential energy will be 0. So what is total energy? Total energy is equal to potential energy plus kinetic energy is equal to 0 plus, what is the equation for the kinetic energy? It is half mv square. But we are changing this v square because we are changing this v square. What is according to the law of kinematics? V square minus u square is equal to what, ma? 2as, isn't it? Here a is acceleration due to gravity. As it is having in a particular height, a is changed into g. Okay, it is changing into g. 2g. S is equal to what, ma? It is equal to h. What is u over here? U, the object is initially in rest. So u will be 0. So we can say v square is equivalent to 2gh. Can we apply over here? Yes. So it will be half m into and 2 got cancelled and the value will be what? mgh. Here mgh at A. And at B it is again mgh. So what we understood? The objects at 2 points are same. Now we have to see what is the total energy of the object at point C. We are seeing. At point C, consider if the object has been moved to a little extent at C. So this is the x, distance which is moved by the object. So what will be this? This will be h minus x, isn't it? Total is h and distance is x. So what will be this one? This is h minus x. So these are the values. So what will be the object at C? At C, potential energy plus kinetic energy. Is the object having potential energy at this point? Yes, because potential energy is not zero at this point. And is the object having maximum kinetic energy at this point? No, the kinetic energy is not maximum because it is again moving, increasing its velocity. So the object at C will be having both potential energy as well as kinetic energy. So what will be the potential energy at C? At C, mg, what is the height, ma? It is not h, instead it is x. mgx is the potential energy. So what will be the kinetic energy? Kinetic energy is equal to half mv square, isn't it? Again, so v square is changing into v square. We have got the value as v square is equal to 2as as u square. U is 0, initial velocity is 0. V is equal to 2as. Here A is changing into G and S is changing into what, ma? S is changing into H minus X. Why? Because the object is in this position and this much distance it has to travel. So V square is equal to 2G H minus X. We can apply over here. Is equal to half m into 2G H minus X. Here half is there, 2 is there, got cancelled, is equal to mg h minus 6. We can say in other words as mg h minus mg x. Okay, now what is the total energy? It is the sum of potential energy as well as kinetic energy, isn't it? So total energy is equal to, what is potential energy? mgx. mgx plus mgh minus mgx. This got cancelled and this got cancelled. So the total energy is what, ma? Total energy is again mgh. So what you understood? Here at position A, the total energy is mgh. Here at position B, the total energy is mgh. And at any point C, the total energy is mgh. Means what? Total energy of an object remains constant at any point. Okay, so this total energy remains constant. Even though it is splitting into potential as well as kinetic, the total energy remains constant. This is the one which we are learning, and this is very important and will be coming for your question paper as 4 marks or 5 marks. Now we are moving to see about the power. What is power? We are going to see. What is power? Power is the rate of doing work. If the work is done, maximum work is done in minimum time, the object is having high power, we will say. If the work is done by taking much more time, it is having less power, we can say. So this is power. So rate of doing work, that is work divided by time, gives what, ma? Power. What is SI unit of power? Joule per second, isn't it? Joule per second. So yeah, the SI unit can be said as, what is the unit of power? The power is having the unit as watt. WHAT is not, the spelling is WATT. WATT, watt. Watt is the unit of power. What is 1 watt power? When an object is doing 1 joule of work in 1 second, we can say 1 watt of power has been done. Did you get, ma? If an object is doing 1 joule of work in 1 second, we can say 1 watt of power is done. That is commercial unit of energy. That is, energy is not given as little or little and little. It is given in the form of kilowatt hour. What is this kilowatt hour and how can we define commercial unit of energy? All this we are learning here. We know power is what, ma? Work divided by time. The work is equivalent to energy, no? So, energy is equal to what, ma? Energy is equal to power into time. Okay. Now, about the commercial unit of energy. Commercial unit of energy is equal to 1 kilowatt into hour. 1 kilowatt hour. So 1 kilowatt is how many watts, ma? This is 1000 watts, isn't it? Into hour means what? 1 hour means what, ma? 60 into 60 seconds, isn't it? So can you multiply and find the value? It's very easy, right? 1000 watt into 6 into 6 is equal to 36. 36, how many zeros has to be written? 2 zeros, seconds. Is equal to how many zeros are there all together? 1, 2, 3, 4, 5. So, 36 into 10 raised to 5 watt seconds. Or we can say 3.6 into 10 raised to 6 watt second. This is what, ma? This is the commercial unit of energy. 1 kilowatt hour is defined as the energy used in 1 hour at the rate of 1 kilowatt. Energy used in 1 hour at the rate of 1 kilowatt is called what, ma? 1 kilowatt energy. So we can say 1 kilowatt energy is equal to what, ma? 3.6 into 10 raised to 6 joules. Also we can write. Joule is the SI unit of energy, isn't it? So this is 1 kilowatt second is equal to 3.6 into 10 raised to 6. Now this is question time. Be ready for that. The first question is, rock rolling from the hill possesses dash energy. It's very easy, I think. When the rock is rolling from a hill, which kind of energy it is having? Is it potential or kinetic? Second is, what kind of energy is transformed? What kind of energy transformation is occurring in thermal power station? Which kind of energy transformation is occurring? Dash energy into dash energy is the question. In thermal power station. Okay. Third question is, arrow hold on a bent bow possesses dash energy. Arrow is ready to move. The arrow is in the bent bow. Which kind of energy that arrow possesses? Okay. These are the 3 questions. Answer these questions and put it in the comment box and we can discuss. Okay. Bye.